Okay, we are going to look at some properties of polynomial addition and multiplication. Namely, we're going to look at which, if any, of the field axioms are satisfied. So let's try to look at first associativity. So that would be P of x plus Q of x plus R of x. And we'd want to know, is that equal to, with the way in which we've defined addition, P of x plus Q of x first, and then adding on R of x. Now, to add polynomials, remember, we have to kind of do this silly trick of extending by 0. So I'm going to write them all having degree n, where it's understood that they may not all have degree n, where some of them may have been extended by 0. So we can write, we're going to check to see if this is true. We can write our p as a0 plus a1x plus anx to the n. And we can write our q as maybe with b coefficients. And then our r maybe with c coefficients. And that would be our left-hand side. So let's label that. This is going to be our left-hand side. And let's just compute this sum. Now again, it's understood that some of these have been extended by 0. They may not all have degree n, just to be very clear. Okay, so the p is going to stay. I'm going to really abbreviate the p this time. There we go. And then we just combine like terms. And this is why we have to extend by 0, because otherwise we would have weird business with the degrees being off. And this was our fix for that. All right, we then combine like terms here. So our new constant term is going to be a0 plus the constant term of the other guy, which is b0 plus c0. And then we're going to get a1 plus b1 plus c1, and so on. an plus bn plus cn. Great. Now let's look at the right-hand side of the associative law. So that means we are going to go ahead and add add p and q first, so add the a's and b's, the a polynomial and the b polynomial. A lot of writing here, but none of it's necessarily hard. Most of it's just bookkeeping. Oops, extra parentheses. All right, so we have to compute that sum now. All right, so we have to add our a's and b's first. So that's going to be a naught plus b naught plus a1 plus b1 x. And we keep going, combining like terms till we get to that. And then the c comes along for the ride. All right, now we're going to combine like terms for the left expression and the right one. So our constant term is going to be a naught plus b naught in parentheses plus c naught. And then a1 plus b1 in parentheses plus c1, and so on. an plus bn in its own parentheses plus cn. Okay, so that's our right-hand side, all the addition computed. Now, let's point out something, that the constant term of the left-hand side and the constant term of the right-hand side are actually equal. And they're equal because addition in z is associative. So since addition in z is associative, actually all of our coefficients are going to line up. Oh, I'm missing an x here. Oops, there we go. All of our coefficients are going to line up. Since it's associative, what do we know? We know that ai plus bi plus ci is ai plus bi plus ci for all I. Okay. Thus, each one of these coefficients of the corresponding x, they're all equal to each other. So this tells us that the left-hand side equals the right-hand side. All right, so therefore, addition of polynomials is associative. And that's not new. You know that. Everyone, once you get past algebra, you know that it doesn't matter the order in which you add polynomials together. But here is a proof of that. And again, we have to be careful with our extending by 0. So I won't check commutativity, but we could go in and we could check commutativity. And I'm going to say you will. This will also work. Why should that work? Well, addition in z adjoin x, our polynomial, a set of polynomials with integral coefficients, it's just defined coordinate-wise. It's just defined term-wise, right? On each, or I guess the right term here would be monomial-wise. It's defined on each power of the x. You just combine like terms. That's going to be defined in terms of the addition in z, and so since the addition in z is commutative, so is this one. Okay, so you'll use that plus in z is commutative. Right? So you're going to do this one. Okay. Before we go to the next couple, let me point out something. We just used that addition in z is associative to prove associativity. We just used that addition in z is commutative to prove commutativity. So what's special about z here? And the answer is nothing. If we have an object, if we have a set, so note well, if we have a set A with a plus such that the plus is associative, then we can look at polynomials with coefficients in A, this, and have the same addition law. This has associative addition as well. Same as commutativity. Commutativity. I don't know how to spell that. I guess that's an I. Oops. So this is saying that the coefficient set, the algebraic operations there, influence what happens in polynomials. And this should be very much unsurprising. We're just noting it. Okay. Now to finish addition, we have to talk about the zero polynomial, so the additive identity. And we can call it 0 of x, and it's the polynomial which is 0. Or if you like, all of the coefficients are 0. So the 0 polynomial is a perfectly good polynomial, and the 0 polynomial has no non-zero coefficients. So usually what we do, and this will be helpful, this is a definition. So we're just going to arbitrarily set it to something, and it'll be helpful later. We say that the degree of 0 is the smallest thing that you can possibly be. And the idea behind the smallest thing you can possibly be is negative infinity. Now, I think it's pretty clear here that when you take a random polynomial and you add on the 0 polynomial, that's the same as taking that 0 polynomial and adding the polynomial, well, because it's commutative, so it has to be true, and you're just going to get the regular polynomial out of it. So we're not going to check that, but that is the identity, and you will check that. And let's look at now the inverse, additive inverse. So if I have a p of x, then p of x looks like a0 plus a1x all the way up to some an x to the n. Then I think you'll find that the polynomial negative p of x, which is negative a0 plus negative a1x plus negative an x to the n, is the additive inverse. And again, that's really easy to check. I'm not going to do anything there. It's pretty clear when you add these, you get 0. Okay, those are the additive properties. Let's take a minute and let's look at some multiplicative properties. And we could also point out that if our set A had a 0, then you could construct the 0 polynomial, and so the polynomial ring would also have a 0, or the set of polynomials would also have a 0. And if our set A had additive inverses, then this guy would also have additive inverses. So there's nothing special about Z, is what I'm getting at here. All right, so let's look at our multiplicative properties, and this is where things change a little bit. This is what we were calling 5 through 8 in the field axioms. So 5 was associativity. Associativity would tell us that P of x times Q of x times R of x is the same as P of x times Q of x and then times R of x. That is a great exercise to do, and I'm not going to do it. It would take probably another 10 minutes of me explaining, but this is a great exercise. It is in fact true. And one of the things you're going to need with that is you're going to need actually more than just associativity and multiplication. You're going to need some other properties that I'll point out in class. So there's associativity, there is commutativity. That's also going to be true. And the reason why that's going to be true is it doesn't take so much time to explain. But if you write your P of x as a0 plus an x to the n, and if you write your Q of x similarly as b0 plus bm x to the m, where m and n are not necessarily the same, then PQ is some c0 plus cn plus m x to the n plus m. And QP with our addition rule is some d0, maybe different, plus dm plus n x to the m plus n. And these coefficients, these c's, satisfy the following. You look at a0bi plus a1bi minus 1 plus ai minus 1 b1 plus ai b0. That's ci. And then di is a similar thing, except for you start with the b coefficients because q is on the left. So it's going to be b0 ai plus b1 ai minus 1 plus b I minus 1 a1 plus bi a0. So that's what the coefficients for the product in the reverse would be. Now if we look, that term matches that term because multiplication in z is commutative. So we're using commutativity of multiplication in z right now. That term matches that term. That term matches that term. That term matches that term. So actually all of the coefficients of these polynomials are the same. So this tells us then that P times Q is Q times P. Oops. Great. Now that's commutativity. Great. And now 7 was identity. In particular, there should be a polynomial that takes the role of 1. It's the polynomial which is 1 and has all coefficients being 0. Now it's not hard to show. So from this, it's almost it's almost obvious that 1 times p is p times 1 is p. If you look at the second guy, so 1 would play the role of q, for example. So that's a p times q. So it's this product. The polynomial 1 has degree 0, so you just go out to Cn. And the only non-zero coefficient, so the only non-zero b, is b0, and b0 is a 1. So all of these other terms go away if you use q equals to 1. And you're just left with ai times 1, which is just ai. So ci is equal to ai. So that's not too hard to check. This is also true. Inverses. So there's a lot of field axioms. This is a longer video. Inverses. Well, we're going to find that these don't really exist, and there's only very special cases where there's an inverse, and this is kind of unsurprising. Namely, z doesn't have multiplicative inverses. So why should we expect something built from z to have multiplicative inverses? Unless it's plus or minus 1. And so, we could skip this, but I think this is going to illustrate a really cool property. So notice that the degree of p times q is actually degree of p plus the degree of q, provided p and q are in z adjoint x. So why is that true? Well, let's go up. The degree of p is, if we assume an and bm are not 0, the degree of p is n, and the degree of q is m. Cn plus m is an times bm. We saw that in a previous video, which is also non-zero. So p times q has degree n plus m. That's exactly the degree of p plus the degree of q. All right. So suppose you had some p of x in z adjoint x, such that there exists a q of x with p times q equals to the polynomial 1. Well, then you could compute the degree of 1 in two different ways. On the one hand, the degree of 1 is clearly 0. It's a constant polynomial. The non-zero constant polynomials have degree 0. On the other hand, 1 is p times q. So we can look at the degree of p times q. But the degree, we say, is additive. It breaks up under addition sometimes. We'll see that's not always true, but in this case it is true. So what do we have here? We have a non-negative number and a non-negative number, and they have to add to 0, because that's the left-hand side. So this tells us that the degree of p and the degree of q are both 0. So the only way to have two non-negative things adding to 0 is if they're both 0. So p is a constant, because those are the degree 0 terms, and this is some non-zero c and z. Q is also a constant, and we have the product of two constants being 1. Well, that only happens if c is plus or minus 1. So there aren't multiplicative inverses, is what this is getting at. In particular, nothing of positive degree could have a multiplicative inverse. You have to be degree 0, and you have to be the constant polynomials 1 or negative 1. So not a lot of multiplicative inverses. So let me just say don't always exist. And in the interest of time, we're going to just wrap up the last two and then wrap up the point. Shivativity. Called this 9. So that would be p times q plus r. We'd have to check this. It's kind of a nightmare. Is p times q plus p times r. And that's left distributivity. Oops. And then we have right distributivity. So p plus q times r is p times r plus q times r. Okay, so both of these happen to be true. And so what this is telling us is, although we failed to have, I guess the only thing we failed to have is multiplicative inverses, we still have a linking between the addition and multiplication. So what you should take away from this is, well, first of all, we've explored some properties of z adjoint x. And we saw that, well, it is missing multiplicative inverses of non-zero elements. It still has an addition and a dot and a multiplication that are well behaved. Namely, we still have associativity, we still have commutativity, we still have identities, we still have additive inverses. And the distributive properties, both of them, they still hold. So, not only they're well behaved, and they're still linked by the distributive properties. So there's some relationship between them. And what this is saying is, hey, this is still interesting to look at, but we don't have multiplicative inverses. And just this is not like a new thing, right? We saw that Z was a really interesting place to do arithmetic. We didn't have multiplicative inverses, but it was still interesting. And what we're going to do is we're going to see that these not more interesting, but these sort of weaker guys that have an addition and multiplication, they form something nice called a ring. In this case, it's going to be a commutative ring because the order of multiplication doesn't matter. But this is one of the best examples of a ring for some meaning of the word best.